Hey everyone, here's a video on determinants and inverses of matrices. You can reference this information in Chapter 4, Section 4, and Section 5 of your textbook. Alright, so we're going to be looking at determinants and inverses of 2 by 2 matrices. So as we talked about before, matrices, their dimensions are the number of rows by the number of columns. So if you have a square matrix, that means your number of rows and columns will be equal. So every square matrix, which will be n by n, so its dimensions are the same, so they're both n, has an associated value called its determinant, shown by straight vertical brackets such as 1, 2, 3, 4, and you can see here that they have the vertical brackets. The determinant is a useful measure, as you will see later in this lesson. To find the value of a determinant, it will just be a single number. You can write it either as DET with the little square brackets, or you can have the vertical line brackets to show you are taking the determinant. Either of these things, those are equivalent. But to find the determinant, you take the first diagonal and multiply those things together, and then you're going to subtract the product of the other diagonal. So here we'd have 1 times 4 minus 3 times 2, and that's negative 2. So our determinant for the matrix 1, 2, 3, 4 would be equal to negative 2. The determinant of matrix A may be denoted as determinant A, or, again, those vertical line brackets around the A. So don't confuse that with the absolute value notation. That's not the same thing, and you won't have to worry about that with matrices, so don't be concerned as far as getting those confused. Okay, so to find the determinant of each matrix, here we have the matrix 1, 5, 4, 8. It is a 2 by 2 matrix. It is a square matrix. And so we take the first diagonal, multiply it, and then subtract the other diagonal multiplied together. So we'll have 1 times 8 minus 4 times 5, which is 8 minus 20. So here our determinant is negative 12. Let's look at another example. So here we have some fractions, and we also have pi, and that's okay, it's just a number. So we would take the difference of the cross products here. So 1/2 times 2 pi is just pi, and then 4 times 1/8 is just 1/2, so pi minus 1/2. And you can actually leave your answer like that instead of having to write numbers out and simplify them. So pi minus 1/2 is our determinant. You really won't have a lot of problems that involve pi, but it's just showing you that you can have other numbers besides just whole numbers in your matrix. Okay, so we can have an inverse only if it is a square matrix. But not all square matrices have inverses. So let's just look at this little paragraph here. When we evaluate the product of 2 and its multiplicative inverse 1/2, it will give you 1, right? So 2 times 1/2 equals 1. So what we're looking for is what are we going to multiply our matrix by, so that way its multiplicative inverse, a to the negative 1, that just means the inverse of a, will give you the identity matrix. The identity matrix, by the way, it has a bunch of zeros in it, except the main diagonal here it has 1s, but everywhere else will have zeros. So if it were just a 2 by 2 matrix, that would just be these top left 4 values, the 1, 0, 0, 1. But if you wanted to expand it some more, you just keep adding 1s down the diagonal. Okay, so let's look at this inverse of a 2 by 2 matrix. So we're trying, here's our formula here, and so we have the inverse of A equals 1 over the determinant of A. And remember, that's just the difference of the cross products of our diagonal. And then you'll notice this matrix is like a little bit flip-flopped. So notice before it was A, B, C, D. Here, the A and the D got switched, and the other diagonal got multiplied by negative 1. So sometimes I just call this the flip-flop matrix, and it's nothing very correct, I guess, to say mathematically, but you flip the first diagonal and then switch the signs on the second diagonal. If the determinant is 0, then 1 divided by 0 is undefined. So if it has a determinant of 0, then that matrix will not have an inverse. It will not have something that when you multiply it, you will get the identity matrix. And we just call those a singular matrix if they have no inverse. So let's find the inverse of this matrix if it is defined. The first thing we need to do is figure out the determinant. So we'll do 4 times 1 minus 2 times 3. And so we'll get 4 minus 6 is negative 2. Our determinant is negative 2, so we know it has an inverse. There's a matrix that we can multiply by to get the identity matrix with the 1s and the 0s. So the inverse of a, just using our formula, a to the negative 1, that's how we note an inverse, is equal to, so we'll have 1 over the determinant. So here that's our determinant of negative 2. So 1 divided by negative 2 is negative 1/2. And then times, here's our flip-flop matrix. The first diagonal got switched, and the second diagonal was multiplied by negative 1. And now we just have a scalar that we're going to multiply everything by. So 1 times negative 1/2 is negative 1/2, and negative 1/2 times negative 3 is 3/2, and so on. So our inverse matrix is negative 1/2, 3/2, 1, and negative 2. And even though we won't be concerned with multiplying these two things together, if I were to multiply the original matrix by this inverse matrix, it would give me the identity matrix of 1s on the diagonal and 0s everywhere else. Okay, so let's find the inverse of this matrix if it is defined. So 4 times a fourth is 1, and negative 3 times negative 1/3 is 1. So 1 minus 1 is 0. And if the determinant is 0, then it does not have an inverse. So this matrix does not have an inverse. It is a singular matrix. Let's find the inverse of 3, 2, 3, negative 2. So make sure the determinant is not equal to 0. So 3 times negative 2 times 3 times positive 2 is you'll get negative 6 minus 6, and that equals negative 12. It's not equal to 0. That tells us that this matrix has an inverse. So we'll do 1 over the determinant. So 1 over negative 12 is negative 1/12. And then we'll switch the first diagonal. So it used to be 3 in the top and negative 2 in the bottom. So we switch those two. And then we switch the sign of the other diagonal. So those are now negative 2 and negative 3. At this point, we just multiply by this scalar here. And so our scalar product will get 1/6, 1/6, 1/4, and negative 1/4. So the inverse of this matrix, 3, 2, 3, negative 2, is 1/6, 1/6, 1/4, and negative 1/4. And that is it. I will answer some more questions for you in class, so let me know if you have any, and I hope you have a great day. Bye.